Nihal, you win the prize. It seems that no matter how early I check into the class, there's always somebody here. And you're the first one today. Punctuality is a good thing. There are not too many people here today. Am I just early? Hey, while we're waiting for people to gather, let me just say I have often been meeting with people on Friday after class, have an office hour after class, but today I cannot do that. I have to leave town as soon as we're done. I will also say that some of the students that I was talking to this morning were concerned that my marker is getting hard to read. I think the markers are all drying out. And I think I'm running out of paper. So apparently we're getting near the end of the semester because everything is starting to fall apart. Well, I hope you guys are not falling apart. We have been dealing a lot with these indices and so on, using the primitive roots to prove things and to do some calculations. But actually, we can prove things without, we don't always have to find the primitive root. If we can just show that they exist, then we can prove some of the things that we need. And I did that with you at the end of the class last time when I started discussing the squares mod p. And that's what we're going to continue to do. We'll be talking about squares, and in particular moving into chapter 11, where my goal probably won't get to it till Monday, is to a proof of what's called quadratic reciprocity. So this is a theorem, a lovely theorem. It goes all the way back to Gauss, who he himself loved his theorem so much he gave quite a few proofs. But what it allows us to do is actually go through some calculations to decide very quickly whether or not a number is a square modulo p. And then I'll be discussing a little bit of how that turns out to be useful for us as well. So my technique for addressing some of these things does build on what we did with the primitive roots, the orders of elements, and the indices of elements, mod p. So I have a little formula that I'm going to use, and I want to prove it and take this opportunity just to kind of summarize what all those words are, especially when we're dealing mod p. So let's turn this around. One moment. Sorry. All right. It seems stable now. All right, so as I said, I wanted to give one sort of computational tool that links together these different ideas, these different numbers that we've been computing. So we have been discussing the order of an element A, mod n in general. This only applies if A is an invertible, or all of these assume that A is an invertible element mod n. And then once we have a primitive root, we could talk about the index modulo R of A. This only exists if there is a primitive root, and as we decided that means that n has to be the power of an odd prime, or it could be 2 or 4. But I will assume that in everything that follows today, that the n is actually going to be an odd prime. So that way I'm sure that there is a primitive root. So these are just two integers that you can compute for the number A. And the reminder is that this one here is the least k that gives A to the k power congruent to 1 modulo n. And this one is the index I that makes A be congruent to R to the I. So two exponentiation things, but A shows up in different places in the two formulas. Okay, so here's the result that links these. I'm going to phrase it this way. If you take the order of A mod P, and you multiply that by the GCD of the index mod R, or base R, and P minus 1, then that's P minus 1. Now that's a big mouthful, and really what I want you to see from this is that if you know the index of A with the base of R, whatever the primitive root R is, then by taking the GCD and dividing it into P minus 1, you could figure out what the order of A is. That's the part I really want out of this. But I wrote it out as it's a statement of a product of several, using several positive integers, so I thought this would look a little more succinct. So let me show you the proof of this one. You know, I taught a real analysis class last semester, and one of the things I pointed out to the two students is that when you're in high school, when you wanted to show that two numbers are equal, you just keep manipulating some algebra until the left-hand side looks like the right-hand side. When you're in the real analysis class, the way that you show that two numbers are equal is actually by showing that the distance between them is less than epsilon for every positive number epsilon. So there's some kind of limit arguments involved. And in our class, the way I'm going to show that two numbers are equal, positive integers are equal, is to show that each one of them divides the other one. Or each one of them is greater than or equal to the other one. That's the same in this context. So that's what I'm going to do. I'm not just going to manipulate the formula on one side until it looks like the other side, but I'm going to give you two separate parts to the proof to give the two inequalities that I need. So let me first show you that the left-hand side is smaller than the right-hand side, and in fact, I will show you that P minus 1 actually divides this left-hand side. And the proof for that is simply to raise both sides as exponents on the number r. Because obviously if you take r to the p minus 1 power, you know that that's congruent to 1 mod p by Fermat's theorem, or from the Euler theorem. On the other hand, well, and in fact, if r is a primitive root, I'm going to need this. If r is a primitive root, then p minus 1 is supposed to be the smallest exponent that makes this be true. On the other hand, I am going to show you that if I take r to this whole left-hand side, that will also be 1. So I'm going to show r to the left-hand side is congruent to 1, and the conclusion will then be that the left-hand side is greater than or equal to the order of r. So the order is supposed to be the least exponent. But if r is a primitive root, then this order was supposed to be p minus 1. So the p minus 1 will be smaller than the left-hand side, and it actually will be a divisor. Okay, so how do I know that this is true? Well, for this direction, what I'm going to use is that Bezout description of the GCDs. So let's write this GCD that shows up in this line as being a multiple of the index and a multiple of p minus 1. And then if I raise r to this exponent, sorry, I raise r to this left-hand side exponent, left-hand side, that's now equal to, well, it's exactly what you see here. Here's the GCD factor, and the other factor just says order of A. So I'll write that in here. We have alpha times the index of A times the order of A, plus beta times p minus 1 times, again, the order of A. And this is now using the laws of exponents. I will write this as a product of two powers of r. But here what you see is r to the index of A. R to the index of A is exactly what A is. That's the definition of index. Oops, sorry, it's not visible. The index of A is the exponent I exactly that you need that gives you an A when you calculate this exponent. So you have A raised to the order of A power raised further to the alpha power. And this other factor is easy. It's r to the, well, it starts with r to the p minus 1. Oops. Then there's all these other exponents up there. But I don't need to know exactly what they are. I don't have to pay attention to that because a to the order of a power, this order is the least exponent that makes this quantity equal to 1. And likewise, as I said earlier, from the Fermat theorem, we know that what's inside this exponent is equal to a 1. So I got what I wanted. When I take r and I raise it to this exponent that you see on the left-hand side, you will get a 1. So this whole left-hand side has to be actually a multiple of p minus 1. It has to be bigger than p minus 1. Now, to go in the opposite direction, that was giving, I'll just say less than or equal to. That's really all I need here, less than or equal. To go in the opposite direction now, I'm going to use exponentiation with a as the base instead of r as the base. So now I'm going to show the left-hand side is less than or equal to p minus 1. And my thinking here is that the order of a was supposed to be the least exponent on a that will give me something congruent to 1. So I'm going to show you that I get a to a power congruent to 1 for something else. And that something else will then have to be at least as big as this order. And the specific thing I want you to consider is I'm going to take a to the power of this quantity on the right divided by this quantity over here. P minus 1. Can I just write GCD for brevity? Now you know that that is an integer because one of the things you're taking the GCD with is p minus 1. So this GCD is a divisor of p minus 1. So this is an integer. All right, but use the definition of index to say, well, a can be written as r to this index of a power. So this is r to the index of a power, and all of that is now raised to the power of p minus 1 over the GCD. Well, the thing is that GCD was not, it's not just a divisor of p minus 1. I mean, look at it, it's also a divisor of exactly this index. So yeah, you see two factors multiplied together, but the GCD is actually dividing both of them. So I'll put the GCD on this factor now. I'll just say GCD again. And then the fact that this GCD does in fact divide that index means that all of this stuff is an integer. So you just have the number r raised to a p minus 1 power raised to some other integer power. And again, r to the p minus 1 power is congruent to 1. Any power of that is congruent to 1. So I have located an exponent that I can put on the a that gives me something congruent to 1. And therefore, the definition of the order says that the order of a is less than or equal to whatever other exponent you find that gives you the congruence of 1. And when I multiply by the denominator in here, what I've just decided is that now the left-hand side is less than or equal to the p minus 1. So when you compare these two inequalities, of course, well, if you compare these two inequalities, that says the left-hand side and p minus 1 are actually equal to each other. Okay, so this is one statement that puts the order and the index together. And along the way, I'm using this proof in part to help you remember exactly what those terms mean. But I do have a particular application in mind, and it's a variant of the proof that I gave you for the same thing last time. A corollary to this is that the number A is the square of something else, mod p. So the wording there is it is a quadratic residue, mod p. So that is saying there exists another congruence class B with B squared congruent to A. And that happens if and only if the index of A is even. Which, by the way, I should point out, it's a little bit funny that I could be making these statements without ever knowing what the primitive root is. This primitive root should be mentioned down here as well. The conclusion, what you discover after reading these theorems is that actually whether or not the index is even, or whatever its GCD with p minus 1 is, those are independent of knowing which primitive root you've chosen. There's usually lots of primitive roots, so it kind of doesn't matter in the statements of these theorems. And so the proof of this is that if A really is a square, if A is the square of B, then that implies that the index mod R of A would be twice the index mod R of B. Now the index is not necessarily, well, I guess it is a positive integer for us. I was going to say that it should be interpreted as an element of the integers modulo phi of n. In our case, the integers modulo p minus 1. But p minus 1 is even, because I did say p was an odd prime. P minus 1 is even anyway, so to say that this quantity is even, it's the same as saying that you have an even congruence class modulo phi of n. So whether you think of the index as being an integer or a congruence class, then it's clearly even. On the other hand, in the converse case, if the index is even, then you have an even number in this slot, and p minus 1 will also be even. So that makes the GCD be even as well. It's going to have to be greater than or equal to 2. And so from this theorem, we now know that the order of A is at most p minus 1 over 2. In fact, it's a divisor of p minus 1 over 2. So that means if you, what am I trying to say here? Oh, wait, I guess I didn't actually need the theorem for this corollary. This is actually the result that I was going to use in a second. So hang on to this thought. So to be a quadratic residue requires that the order of A actually be a divisor of not just p minus 1, but p minus 1 over 2. That's how you can detect the perfect squares mod p. I guess I didn't actually need the theorem now that I'm looking at it. If A is a square, then you conclude that the index has to be even, but conversely, if the index is even, if the index of A is, it's say 2n, then that means that the number A can be written as the primitive root to the 2n power, which is now obviously a square. So those are the two halves of the statement of the corollary that proves the corollary. And I'm sorry, I got a little distracted here because this is the result that I'm going to be using in a second. I put it in here, but it's not really part of this proof. All right, so why do I want to have this business with the indices and the powers, the orders of the elements? It's because I'm going to do I'm going to define another symbol, another integer that we can compute. It's an easy one though. It's just what we would call an indicator function. This is called the Legendre symbol. And assuming that if you've fixed an odd prime p, then it's a number that you associate to to any integer, which you can reduce mod p, and it's computed this way. First of all, the notation is you put the number a on the top of a fraction, and you surround the fraction with parentheses. I'm sorry, it's an old-fashioned notation. We're kind of stuck with it. But you have to understand that this is not really asking you to compute a fraction. It's not a binomial coefficient. It's just another similar-looking notation. But it's an easy thing to compute. It means one of three different things. First of all, it just means a 0 if p divides a. But for numbers that are not divisible by a, those would be the invertible congruence classes modulo p. This is going to be either a +1 or a -1. And we write it as a +1 if p is a quadratic residue. Sorry, if a is a quadratic residue. And it's a -1 if a is not a quadratic residue. It's actually called a quadratic non-residue. So that's it. It's unless it's a 0, it's just a + or -1. Sounds kind of lame, but it actually has some nice properties that we can deal with. And in particular, once we get the law of quadratic reciprocity, we're going to be able to compute this without having to kind of scan all the possibilities for b. I should say here, this is if there exists a number b, if there does not exist a number b. All right, so the first proposition about this is that, well, you could compute this Legendre symbol if you had time to kill. Namely, this Legendre symbol can be computed as just a power of a. We take a and we raise it to the p-1 over 2 power. That's the reference to the p-1 over 2 that I had a second ago. There we go. I'm using my papers. Of course, this is to be computed modulo p. So, well, there's only 3 different cases. We have to decide whether we get the 0, 1, and -1 in the 3 different cases. Obviously, if p divides a, that means that a is congruent to 0 mod p, and therefore any power of a will also be congruent to 0 mod p. So that one's a no-brainer. If, in the next line, if you know that a is congruent to the square of some other congruence class, mod p, then when you compute this power, a to the p-1 over 2 power, that's b squared to the p-1 over 2 over 2. So that's just b to the p-1 power, and by the Fermat theorem, that will be congruent to +1. So in this case, we're definitely getting a plus sign. Now, what about if a is not a square modulo p? Well, we do know how to get something that's congruent to, well, we know that if we take a to the p-1 power, that would give us something congruent to 1, but I'm not asked to take a to that power. I want something to just half that power. Well, this is a congruence class mod p, which by exactly this kind of a calculation, its square would be congruent to 1 modulo p. So this is a square root of 1 mod p. And if you're working modulo a prime, there's only two possible squares. This is congruent to either +1 or -1 mod p. Well, if I did have a to the p minus 1 over 2 power, and that was congruent to 1, then that would mean that the order of a modulo p would be a divisor of not just p minus 1, but p minus 1 over 2. And that's the result that I mentioned in the middle of that proof of the previous one, that was calculating the order in terms of the index. And in this case, that would tell us that the index has to be even. It has to have a GCD with p minus 1 that's a multiple of 2. The index of A has a GCD with p minus 1 that's a multiple of 2. I keep saying less greater than or equal to 2. It's actually a multiple of 2. And therefore, now you know the index is even. And because of the corollary that I just had, now that you know that the index is even, that implies that A actually is a square mod p. We already knew that sort of the converse of that up in this case. When you had a square, you knew you would get something that's congruent to 1. But if you had a non-square, we would have just obtained a contradiction over here. So for a non-square, that means, well, you're not supposed to get a 1. And at the end of the previous page, I said, well, you either were going to get a 1 or a -1. So if it's not 1, then that means that this power has to be congruent to -1. So this Legendre symbol is, it's just like a fact-finding device. It helps you, I mean, it doesn't help you do anything. It just keeps track of the fact that you, some of the elements mod p are squares and some of them are not. But it can be thought of as being the result of a large calculation. You take this number a to some enormous power and see whether you get 1 or not. You could only get a 1 or a -1. Okay, so using this form of the Legendre symbol, I have a few things that I can say. One of them is a repeat of a result that we've proven in a different way. So here's a corollary to this proposition. It says, I'll write it this way: A mod p, the Legendre symbol of A mod p times the Legendre symbol of B mod p is the same as the Legendre symbol of A times B mod p. In other words, the Legendre symbol for a fixed p is actually a multiplicative function. We've talked about multiplicative functions. You don't even need to know that A and B are co-prime in this case. It's really just a question of whether or not A and B are prime to P. If either A or B is a multiple of P, then you'll have a 0 for one of these two factors. But of course, if A or B is a multiple of P, you'll have a 0 on the right-hand side as well. So the only cases of interest are the cases where A and B are both invertible mod P. And for those, we had a discussion last time about how to decide whether something is a square of mod p or not. Let me show you the calculation I want to do here, and then I'll remind you of how we said it last time. If you use the previous proposition, here's the proof. This left-hand side is a to the power of p minus 1 over 2 times b to the power of p minus 1 over 2, and the right-hand side is AB to the power of p minus 1 over 2. And so this is nothing but your law of exponent, one of your laws of exponents. The product of two like cubes or whatever is again another cube. And well, this is not too surprising of a result in, and let's call it 3 cases out of 4. I mean, if you knew that A was the square of something and you knew that B was the square of something else, then obviously AB would also be a square. So when that's a 1 and that's a 1, of course you get a 1. Almost as trivial is the statement that if A is a square but B isn't, that means that AB cannot be a square, because if A is a square and AB is a square, well, then that would imply that B is, let's see, it would have to be x inverse times y squared. I mean, I've already ruled out the case where anything is a multiple of P, so we're just talking about invertible congruence classes. So if AB is an invertible congruence class that it's a square, I'm sorry, if this one is an invertible congruence class that it's a square, then X itself has to be invertible. And if you calculate this quantity and square it, you'll have something which, when you multiply it by X squared, you get Y squared. So if A is a square and AB is, then B also has to be. If A is a square and B isn't, that doesn't leave any room for AB to be a square. And of course, similarly, if you knew that B was a square and A wasn't, then AB could not be a square. The one that's kind of surprising is the one that says if this Legendre symbol and this one also are both equal to -1, well, -1 times -1 is +1. It simply says that the product of two non-squares is always a square. And from this formula, from this kind of a description of the Legendre symbol, that's obvious. But you shouldn't think that it's obvious, because saying that something isn't a square doesn't really tell you what it is. It tells you what it isn't. It isn't a square. And just to drive home this point, let me point out that if you weren't working modulo a prime, this wouldn't be true. A prime power, as it turns out, an odd prime power, then it would be okay as still. But if you try to compute the Legendre symbol, use the same definition of the Legendre symbol in the case where the number in the bottom is a composite, like let's say 15, then you could take two non-squares modulo 15, and their product would not have to be a square either. You could have a -1 and a -1, and the product would also be a -1. So writing things out as this plus or -1, it makes perfect sense for a prime modulus, because we can prove that things work out, that the product of two non-squares is a square. But just to write down that quick example, if your modulus is obviously not a prime, but 15, then let's see, you could take a number like take the number, I think 7 is a square. Hang on. Let me tell you what calculations I'm doing in my head. Let's take a number which is, take a number A, which is congruent to 2 modulo 3, and yet it's congruent to have it be 1 modulo 5. Can we find a number like this? How about 11? So 11 is not a square. And I know it's not a square mod 15, because how could it be a square mod 15 if it's not even congruent to a square modulo 2? Modulo 3, the only square is a 1. On the other hand, you could take a number like, let's take B to be a number that's congruent to 1 modulo 3, all right, but I'll have it be congruent to 2 modulo 5. So an example of that would be a number like 7. So then B modulo 15, that's also a non-square. 7 is not a square mod 15, because how could 7 be congruent to a square mod 15 if it's not even congruent to a square modulo 5? I'll let you check all the possible squares modulo 5, and they are just, well, 0 and 1 and 4. None of the squares is congruent to 2 mod 5. So no integer can be congruent. The square of no integer is ever congruent to 7 mod 15, because they can never even be congruent to 7 modulo 2. All right, well, having found the A and the B that are both non-squares modulo 15, what did I say A was? A was 14, no, 11. 11 is 1 more than a multiple of 5 and 2 more than a multiple of 3, yeah. And the b is equal to 7. Well, if you multiply a times b, obviously that's 77, but that's congruent to 2 mod 15, and that's not a square either. And the reason I know it's not square is because now I can work modulo either modulus. This 2 can't be a square mod 15 because it's not even a square mod 3. It can't be a square mod 15 because it's not even a square mod 5. It fails on both counts. So we have a funny kind of a situation where 11 mod 15, that's a -1, and 7, the Legendre symbol of 7 modulo 15 is also a -1, and yet that's not going to be the product of taking the Legendre symbol of 77 modulo 15, because this one is a 1. So be thankful when we're working modulo a prime, okay? Because you're getting this cool result that says it's just all about the Legendre symbol, and the Legendre symbol is multiplicative. The product of two non-squares is again a square. All right, so I want to think a little more in detail now about exactly which numbers are squares modulo p. When can I solve a congruence like x squared is congruent to a modulo p? And a kind of a starting point is, let's take this, this kind of a problem. How would you compute the Legendre symbol of -1 modulo p? For which prime, for what odd primes p is -1 a square mod p? Now don't tell me -1 can never be a square, because you're thinking of real numbers here. Obviously, when p is equal to 5, then -1 is congruent to 2 squared, so it is a square modulo p. And the answer is, it depends on how p falls modulo 4. This Legendre symbol is going to be either a +1 or a -1, depending on whether or not p is 1 more than a multiple of 4 or 1 less than a multiple of 4. So this is a good special case to remember. After we've set up everything else, then this is actually not hard to prove, because I've already said that the Legendre symbol can be simply computed by taking a power of the number whose quadratic character you're wondering about. So we, in this case, are simply raising the number -1 to a large exponent. Well, as you know, you're either going to get a +1 or -1, depending on whether this exponent is even or odd. And in the case where p is a 4n plus 1, this exponent turns out to be a 2n. And then when p is 4n minus 1, you'll have 4n minus 2 over 2. This is a 2n minus 1. So this one is even, and this one is odd. And therefore, these powers are exactly the numbers that I've written down here, +1 or -1. So, well, this tells you two things. It tells you that if you have a prime that's 1 less than a multiple of 4, it will be impossible to ever have x squared congruent to -1. So the corollary for this is that there does not exist an x whose square is congruent to -1 mod p if p is 1 less than a multiple of 4. But, okay, that's just restating the same thing. But it's actually interesting to think of how exactly this one plays out. It has other consequences. Again, let's just keep this premise that p is 1 less than a multiple of 4. Not only can no square ever equal -1, you can never find a pair of squares that are negatives of each other. Well, you can, of course, if x and y are both 0, then 0 squared is the negative of 0 squared. I get that. But among invertible pairs, x and y, you'll never be able to find the two of them be negatives of each other. And the reason for that is because if you could find this, a solution to this problem, then if you calculated y inverse times x, that would be a congruence class whose square would be congruent to -1. So you will never, when you list all the squares mod p, you only have to find, how should I put it? For every pair of congruence classes mod p, pair them off with a congruence class and its negative. So for example, it's the smallest prime of this sort, other than p equals 3. Let's try p equals 7. When you list the squares, you can square just the numbers 0, 1, and 2. Sorry, 0, 1, 2, and 3. You don't need to start squaring 4, 5, and 6 because those are the negatives of 1, 2, and 3, and therefore they have the same squares as 1, 2, and 3. So these are the only squares. These are the only invertible squares. And what you should notice is that here, other than 0, I've listed exactly half the elements of the integers mod 7. The ones that are missing are exactly the negatives of these. So 6, 3, and 5, those are the non-squares. So you never have two numbers that are above each other in my little display here. These are two numbers that add up to 0 mod 7. You can never have both of them be squares. Either the one on the top is the one that's always the square, and the one on the bottom is the non-square. So you can't ever make, well, let me rewrite it. You can never make a sum of two squares be a multiple of p. That doesn't say anything different from this. You cannot find two integers x and y that have x squared plus y squared congruent to 0 mod p, except of course if x and y are both 0 mod p. If you take away the language of congruence, another way to say this is you can never find two integers for which p divides the sum of those two squares, except of course in the case where x and y are both 0 mod p, so unless p divides x and p divides y. Obviously if p does divide both x and y, then p will divide this quantity here. But you can't ever have a prime even dividing a sum of two squares. Now this ties in a little bit to what we were doing on the exam. On the exam I had you think about the numbers that could be written as a sum of 3 squares. If I ask you to think about the numbers that are only sums of 2 squares, well, every square is congruent to either 0 if x was even, or 1 mod 4. So when you add two squares together, that means that x squared plus y squared can only be congruent to 0, 1, or 2 mod 4. So just like the problem that I gave you on the exam, if I had asked you which numbers could be written as a sum of 2 squares, you could have told me, hey, no number that's ever 1 less than a multiple of 4 is ever going to show up in this way. But what we've done here is to show you can't even get a sum of 2 squares to be a multiple of such a prime p. Forget about trying to get this prime p as a sum of 2 squares. You can't even get a multiple of p to come out to be a sum of 2 squares unless you do the dorky thing of squaring 2 multiples of p in the first place. So this is a very strong statement that generalizes an observation that you could have made on the way during your last exam. I'm going to give you another consequence of this result, still staying with the primes that are 1 less than a multiple of 4. I'm going to tie this into something we did way at the beginning of the semester, which is we looked at a different ring, not the ring of integers, but we looked at the Gaussian integers. Remember the Gaussian integers? This was a set of numbers that you could add, subtract, multiply, and divide, and so it made sense, well, add, subtract, and multiply anyway. And so then it made sense to ask which integers divide which Gaussian integers divide which other Gaussian integers. And well, with that language, we could talk about whether something is prime or not. And I told you guys, although I didn't prove it completely, I told you that you could recreate the division algorithm, the Euclidean algorithm, all that stuff, and actually test for GCDs And you eventually would be able to prove the fundamental theorem of arithmetic in this setting as well. Okay, we had that long discussion, and one of the things we observed is that some numbers stay prime, some prime numbers stay prime in the Gaussian integers and others do not. And what we've just shown here is that these primes that are congruent to -1 mod 4, they stay prime in the Gaussian integers. So I'm going to write that in as a theorem. All these last two pages have all been about primes that are 1 less than a multiple of 4. That's if P is congruent to -1 mod 4. If it's a prime in the ring of integers, then it's also a prime in the Gaussian integers. Because, let me remind you of how we had Euclid's description of primes early in the semester. If you thought that P was not a prime number, let's see, how do I want to say this? P is a... no, skip the Euclid thing. Let's write it this way. If P is not a prime, P would have a factor. And by a factor, I mean something other than a unit. Remember, the units are plus or minus 1 and plus or minus I. But a proper factor would mean it's some number of the form x plus yi, where you don't have a 0 and a 0 for one of those two integers and a plus or minus 1 for the other one. So if this is something that divides P in the Gaussian integers, then if I take complex conjugates of both sides, that would mean that x minus yi would also divide P. Well, you would actually be able to write P as a product of two factors. One of them would be x plus yi, and the other is x minus yi. And so then you would have P expressed as a product, x plus yi times, x minus yi. And of course, if you expand all this out, now you have just two integers, x and y, with P equaling the sum of their squares. And as we've already shown, that's a contradiction. So the primes that are 1 less than a multiple of 4, the ordinary primes, in the ring of Gaussian integers, they stay prime. So 3 is a prime among the Gaussian integers, so is 7, so is 11. The companion theorem to this is about the other odd primes, P. So let me give you that one. If P is congruent to 1 mod 4 is an ordinary prime, then P is not prime in Z bracket I. And in fact, I'll tell you how you can actually factor it. Actually factoring that number P would mean finding two integers like this, x and y, such that P is written as this Gaussian integer times that Gaussian integer. So you would need to have P expressed as a sum of two squares. Now I'm going to show you actually how you would find those two squares. Well, I'll put that in here. It's actually an equivalent statement to what I just wrote. All the primes that are 1 more than a multiple of 4 can be written as an actual sum of two squares of ordinary integers. Which, by the way, if you read this equation modulo P, now you've come to a situation where x squared is congruent to -y squared. And if you bring the y to the other side, you would actually have found a square root of -1 modulo P. So you would actually be demonstrating that -1 is a square in this case by literally finding out what the x and y are. And my rationale here is the proof would just use, the proof of the theorem would say, okay, if you know that P is congruent to 1 mod 4, then one of our earlier theorems today guarantees that you could at least get you know that -1 is a square modulo such a prime. So here's the Legendre symbol. So -1 is a square in this case, well, for such P. which means that there does exist an integer x that has the feature that x squared is congruent to -1 modulo p, or in other words, x squared plus 1 is congruent to 0 modulo p. Well, that means that p divides x squared plus 1. You can find another integer to multiply p by to get x squared plus 1. Now, if I write that out in the Gaussian integers, that allows me to factor this right-hand side as x plus I times x minus I. So if you thought that p was a prime, well, if it's a prime, then anytime a prime divides a product, it has to divide one of the factors. Do you see the ordinary prime p dividing this factor? I don't. In order for this one to be a multiple of p dividing x plus I, say, would mean that x plus I could be written as p times another Gaussian integer, but then you would have a multiple of p for the x, and you'd have a multiple of p for the where the 1 is, the coefficient of I. So that's a contradiction. So this p cannot divide that factor, and similarly it doesn't divide that factor, and so that means that p is not prime. Well, on the other hand, if p does divide this product, then it will have to have a GCD with, if it doesn't divide either of the two factors, it has to have a GCD with both of them. You're actually going to be writing out p as a product of two other Gaussian integers, an a plus bi and an a minus bi, that could actually be found by the Euclidean algorithm. A plus bi would be the GCD of p with x plus I. So now you have to actually compute a GCD in the ring of Gaussian integers. I talked about that early in the semester, but I didn't really do the examples. But you can. You have to refine the algorithm just a little bit to do the computations in the Gaussian integers. The book actually has a summary of that. And once you've computed this GCD, you have, well, it's a divisor of p, it's a factor of p, and it's the factor that divides this x plus I over here. So then the other factor has to be its complex conjugate, and that then tells you that p is written as a sum of two squares. So these are some definitely non-trivial results that you get out of just following the concept of what things are squares and which ones are not. As you can see, I'm starting to lead you here into what are called Diophantine problems. I write an equation that has some known quantities and some unknown quantities, and I ask you whether or not there's solutions in integers. And one of the things we found is that this particular equation has no solutions if p is a prime that's 1 less than a multiple of 4, but it definitely does have solutions when p is a prime that's 1 more than a multiple of 4. And I've actually indicated, there's details you would have to code carefully, but I've actually indicated an algorithm that you could use to find that expression. Okay, so that's the question of whether or not -1 is a square modulo p. I kind of beat that one to death. What I'm going to do next is, I'll do 2, and then 3 and 4. No, after I decide whether or not 2 is a square modulo p, then I'm just going to start focusing on the odd primes and decide when they are squares modulo another odd prime. And that's called the law of quadratic reciprocity, and we'll see that that actually allows for a lot of quick calculations. All right, you guys are getting quieter and quieter as the semester goes by. Any comments or questions? All right, thank you for your patience. This is actually cool stuff. Start reading chapter 11, and I'll give you the quadratic reciprocity when we get back from the weekend. All righty, guys, see you on Monday.